What if we were charged with the task of modeling this function mathematically? We see that it's a sawtooth periodic function and that it has a wavelength of 2 pi. We see that it starts here and then goes up to 1, a y value of 1, or a function value of 1 rather, and then indiscretely jumps back down to 0, a function value of 0 at 2 pi. So we see that the wavelength is in fact 2 pi. The wavelength of the period, if you will. Okay? So the first thing we need to do is to find a description of this function over one period. Okay? So we can look at it, and we need to basically find the equation for the line that goes from here to here. We're going to start at the origin and integrate from 0 to 2 pi. That's usually the easiest thing to integrate over. So the function value over that interval, f of x, is equal to the rise over the run. It rises 1 and it runs 2 pi. So 1 over 2 pi times x. And this is good from 0, let's say x, and then less than 2 pi. It's good over that, right? But we want to model this function globally, and we want to model it using the Fourier series because that's what you're going to be asked to do on your exam. And so this of course is modeling the function, but it's only being modeled over 2 pi, and we want to model it over all of the function values. And so let's see if we can come up with a mathematical description using the Fourier series. So here's the Fourier series. I've seen this before. For A0, we've discussed previously that really all we need to find is the midline of the graph, that is the center line of the graph, instead of actually performing this integration, because this integration says to integrate the function over one wavelength is from here to here. So you take this area and then divide by the wavelength, tau, or here, tau. So you find this area, divide by 2 pi, and you would find it, right? You would find what that is. But it's a much easier way to do that is just to find the midline of the graph, the center line of the graph, which is just f max plus f min divided by 2. So we see that the maximum is 1, the minimum is 0, the x-axis. So the center line is just 1/2, right? 1 plus 0 is 1, divided by 2 is 1/2. So right away, without even doing an integration, we can just say that this is equal to 1/2. Okay? For a sub n, we write 2 over the wavelength, which is 2 pi. So that's why it's so convenient to write this notation with the tau, right? Because tau could be wavelength or it could be period for time. If you're integrating over a position space or over a time space, it doesn't matter. It's just a convenient notation. We're going to integrate from 0 to 2 pi to integrate over one wavelength. F of x over that period is 1 over 2 pi, or over that wavelength rather, 1 over 2 pi times x times the cosine of 2 pi over 2 pi is just 1. So this is just the cosine of nx. And that's dx. And that will integrate n equals 1, 2, 3, so on. If we perform those integrations, we will see that in fact those will come out to be equal to 0. Okay? So you remember that we said that those will come out to be 0 whenever it's an odd function, that the even coefficients, which are these, will all come out to be equal to 0. I did not check this graph to see if it was even or odd, but it must be odd because all of the even coefficients come out to 0, because I've done this calculation already and they came out to be 0. The odd coefficients do not come out to be 0, and so therefore the function must be odd. But I'm not hanging my hat on that fact. I didn't actually even test the function to see if it's odd. I just saw that these integrations came out to be 0, and these integrations did not. Okay, so this is 2 pi, 2 over 2 pi. You can do the odd-even test for yourself if you like. 0 to 2 pi. The beauty of the math is the math always works out. You just perform the integrations and it's just going to tell you what's 0 and what's not 0. Okay, 1 over 2 pi times x. Sine. Once again, 2 pi over 2 pi cancels and we just get sine of nx dx. And we evaluate that n equals 1, 2, 3, ... Those will not come out to equal to 0. Those will come out to be actual values. Okay. So B1. And I've done these integrations. It's basically just a calculus 2 problem to do the integrations. And so we won't bore you with the integrations, but you let n equal 1 and then you perform the integration. And then you let n equal 2 and you perform the integration. And you let n equal 3 and you perform the integration. You can use the symbolic manipulating calculator to perform those integrations, or you can do them by hand. Either way, the answers will come out to be the following. B1 will be negative 1 over pi. B2 will be negative 1 over 2 pi. B3 will be negative 1 over 3 pi. And you see that do you see the pattern? 1 over 1 pi, 1 over 2 pi, 1 over 3 pi. So B sub n in general is going to be negative 1 over n pi, right? Okay, so now let's write down the Fourier series that corresponds to these coefficients. So here's the final result is going to come from this. Right, so f of x is approximately equal to a0 is 1/2, so we have 1/2. All of the a sub n's are 0, so these go away, and then we have these. You see you have 2 pi over 2 pi, tau is equal to 2 pi, so these are going to cancel, so it's just going to be a sine of nx each time. So what we're going to have is B1 times the sine of 1x plus B2 times the sine of 2x plus B3 times the sine of 3x. And so on. And you can just keep adding them. We're just going to do 3 terms for the sake of speed. But you could add as many as you want to make the Fourier series as accurately as possible. Okay, so this is equal to, substituting the values in, 1/2 plus, B1 is negative 1 over pi. Okay, so we won't put the plus, we'll just put minus 1 over pi times the sine of 1x, which is the sine of x. And then it's minus again. 1 over 2 pi times the sine of 2x. And you see where this is going, minus 1 over 3 pi times the sine of 3x. That's it. That is the Fourier series for the sawtooth function. I'm going to step aside and give you a clear screenshot. See you next time.